T-minus 10, 9, 8, 7, 6, green board, 5, 4, 3, main engine start, 1, 0, and liftoff of the Delta rocket with Mars Pathfinder. And the vehicle has cleared the tower.
What you just saw was the launch of the Pathfinder mission on the 4th of December of 1996, which landed on the 4th of July of 1997 on the surface of Mars and carried Sojourner, the first rover that would travel on the surface of a planet that wasn't the Earth. In order to be able to collect samples from remote locations, the 6 wheels of the rover were powered by individual motors. The wheels produced a total force of 64.2 Newton and only consumed 8.5 watts for driving. An additional 2 watts were required for the controller and the navigation computer. Sojourner had a top speed of 1 centimeter per second and with its rocker bogie construction could overcome obstacles as high as 30% of its height. This construction was later reused on the following rover missions that went to Mars, such as Curiosity. For steering, the front and back wheels could be turned by 4 additional motors, which allowed the rover to change direction. The central wheel stayed fixed in position. But how do motors work in principle? If you think back to your high school physics class, you might remember that electrons which move in a field exert a motion or a force, which is perpendicular to the field and the motion of the electrons. This can be remembered easily by the left-hand rule. This effect is also used in motors. Here you can see a schematic view of a DC motor. On the outside, shown as a permanent magnet, is the stator, and on the inside in gray is the rotor, the part that will be rotating and where we can extract the power from. When a current is applied to the rotor, it gets magnetized, and as you can see, it always gets attracted by the opposing pole of the stator. The polarity of the rotor has to be switched. This process is called commutation and can be done either mechanically or electronically. We will discuss how motors work in more detail later on in the video. Motors can be distinguished by their power source, which can be either alternating or direct current. For space applications, mostly DC motors are used, as batteries always provide a direct current. These motors then can be further distinguished in servo or stepper motors. Servo motors can be commuted either by brushes, as I said before, changing the polarity, or brushless. Stepper motors work a little differently than I just described. Although they share the same structure and have a stator and a rotor, they can't move in a continuous fashion and rather only in steps. As you can see in this simplified animation, the rotor is always engaged into one of the active stators, aligning itself and advancing for a small amount of degrees. Although for each stepper motor the amount it turns per step is fixed due to the quantity of teeth it has in its rotor, microstepping allows to further increase the accuracy with which the motors can be turned. Microstepping just means that not only one of the stators is engaged but 2, and the rotor stays in a position between 2 of the stators. A disadvantage of stepper motors is that the higher their RPM, the lower the torque you can extract from the motor is. This is due to the magnetic field taking some time at higher RPMs to completely build up. Also, stepper motors can lose steps, which might be devastating for the mission if you don't have an active encoder, which also additionally checks if the stepper motor actually moved to the required position. Far more frequently, servo motors are used. Servo motors are what most people would think of if you tell them about traditional motors, but additionally have a controller and an encoder which can then give feedback to an active control loop to control actively speed, torque, temperature, and several other parameters, which makes them way more versatile than servo motors. The servo motor has two connections, one for powering the motor and one to receive the data from the encoder. This makes connecting the servo motor a little bit more complicated, but yields more reliable results regarding the position. Now I will talk a little bit more in detail how brushless DC motors work. Here you can see a different representation of the same motor shown before. In the center you see the coil to which a current is applied. If you remember from the left-hand rule, you have to use the index finger as the direction of the magnetic field, which is from left to right. Your middle finger is the direction of the current. And with your thumb, you then see the resulting force, which in this case on the right hand side is to the top, on the left hand side to the bottom, resulting in a rotating motion of the rotor. As you can see, the commuter has reached a different brush, reversing the flow of the current in the spool, and with this allowing for a continuous rotational motion with one coil. This motion isn't perfect, and more of the central coils are needed for a flawless motion and constant torque over the entire revolution. Although here shown as a permanent magnet, for real applications the stator is almost always an electromagnet. Now let's switch over to brushless DC motors. Brushless DC motors, in contrast to brushed motors, have the permanent magnet in the rotor and not in the stator. As you can see here, the stator consists out of 3 pairs of separately powered coils, which can be switched on and off to generate the required field to turn the motor. When comparing the just two discussed types of DC motors, we can conclude that the brushed motor design is simpler in its construction, which is a benefit for space application as less things can break. But on the other hand, we have to take into consideration that the carbon brushes are prone to wear and will, if used for too long of a time, break the motor and thus endangering the success of our mission. Brushed motors can still be used, but have to be coupled with a thorough reliability analysis. The reliability analysis will ensure that the lifetime of the motor won't be exceeded by the mission, and that the planned use of the motor won't put it in a state where the brushes might wear extremely fast or faster than expected. Brushless motors, on the other hand, are more complex due to their electronic switching, but don't have any parts that suffer from wear in the same amount that brushed motors do. This makes them the quasi-standard for space applications. On many rover missions, brushed motors are used. As brushed motors have a lot of flight heritage and a lot of manufacturers offer especially adapted versions for space applications of their brushed motors, they are still quite popular. InSight, which landed on 2018 on Mars for example, had the brushed DC motors on board. This is the drivetrain of Curiosity. Many more components, apart from a motor, are required to be able to control the rover reliably. For example, when the power is lost, usually motors don't have any holding force. This would mean that if the rover was on an inclination, it would start to roll downhill. Thus, usually a brake engages as soon as the power is lost in the rover. The brake allows to hold the position of the rover without having to be powered continuously. Usually, the wheels of a rover aren't directly attached to the output shaft of the motor. More commonly, a gearbox is used. The task of the gearbox is it to come from a high RPM and low torque output from the motor and convert it into a high torque and low RPM motion for the wheels. From the fast turning motor, we can now have slowly moving wheels, which move with high accuracy. Traditional gears would consume a lot of space and weight, thus more compact forms of transmission are usually used. Here you can see planetary gears. The central gear is called the sun gear, the outer gear the ring gear, and in the middle you have the planet gears, which are connected over the carrier. In our case, the central sun gear would be connected to the motor. This would lead to a slower turning of the outside ring gear, here shown in red. The red ring would then be connected to the wheels of the rover, transmitting the power of the motor and thus moving the rover. Another compact alternative to traditional gearboxes is the so-called harmonic drive. A harmonic drive consists of three components: the wave generator, a flex spline which will change in shape and is flexible, and the circular output spline. The green wave generator would be connected to the motor. Its rotation deforms the central ring, which will then slowly rotate but will make available a higher torque than the original motor had. Harmonic gears are also very compact. Here you can see the Maxon GP32HD planetary gearbox, which was used on the Curiosity mission. This part was originally designed to be used on Earth and had to be adapted quite extensively so that it could also be used in space and on Mars. The high temperatures and lack of atmosphere pose challenges for the lubrication. Outgassing is an effect where in vacuum or under low pressure, soluble components of the lubricant would turn gaseous and then recondense on different parts of the spacecraft, such as optics. This has caused a lot of trouble for past missions and is to be prevented by the use of special lubricants. Another effect is called cold welding. Usually most metals have a passive oxidation sheet on their surface. Upon wearing this surface layer, as it would happen when the gears touch, the blank metal parts would be exposed and could spontaneously weld to each other, as there is no oxygen to form a new passivation layer. The noteworthy example to mention here is the Galileo spacecraft, which due to cold welding couldn't open its main high-gain antenna, here shown on the top. A lot of testing has to be done with the motors and gearbox that these effects won't pose a problem during the mission. Here you can see the entire drivetrain of the Sojourner mission. The position of the motor is checked by the encoder. Encoders are either relative or absolute. This means they can track the absolute position of the motor or the relative position since the start of the motor. The output shaft of the motor is connected to a planetary gear, which reduces the output of the motor. The output is then further reduced by a harmonic drive, which is then finally connected to the wheel of the rover. In short, when designing the drivetrain, size and weight restrictions are governing the decision making. Planetary gears and harmonic drives can help to reduce size and weight as they are quite compact for the amount of torque and power they can transmit compared to regular gears. An aspect I didn't talk in detail about is friction. All mechanical components which move will experience some kind of friction. This friction has to be overcome by the motor and reduces the total amount of power that can be drawn from the motor. The drivetrain will break down over time. This is inherent to all mechanical components. In order not to endanger the success of the mission, extensive reliability studies are performed before the launch of the mission. In these reliability simulations, it has to be ensured that the entire system won't break down over the planned lifetime of the mission, and that always the parts stay within the specified environment conditions, such as temperature, load, strain, or acceleration g-forces. After having talked a little bit of the mechanical aspects of motors for rover missions, we need to talk about the electronics and how the motors receive the signals, are powered and controlled. What you currently are seeing here are the power electronics of the Pathfinder mission, the launch you saw at the beginning of the video. This board was capable to deliver 10 different voltages to all the required components in the rover. Power conditioning and the transmission of steering signals is the main task of the electronics for driving. But how are the actual signals for the motor created? It all begins with the avionics box. Here is then shown an example, the avionics box of the Kapvik rover. The data from several sensors is evaluated and a suited path for the task chosen. The flight computer usually is a real-time system, meaning that the computation it's performed are guaranteed to be finished within a given time. This is essential as the steering commands for the individual motors have to be controlled in real time. The flight computer then determines which amount which individual wheel will have to be turned at which time. The path of the rover has to be tracked while it's moving, and the steering signals for the individual wheels might have to be adapted. This is a quite computational expensive task. That's why in new rovers dedicated hardware is used for that task, such as FPGAs, field programmable arrays. Here you can see the Xiphos Q6 FPGA, an off-the-shelf FPGA which consumes only 2 watts and is quite capable. Whereas usual programming involves software, FPGAs are hardware programming, where the algorithm is directly written into the hardware, making it very energy efficient. But also ASICs are used, application-specific integrated circuits. For example, the control loop of the motors is one application where these hardware acceleration boards excel at. Using a general purpose GPU for the same task would lead to a drastically higher energy consumption. The control loop has several inputs and is more complicated than shown here. The control loop has to ensure that the maximum torque, speed, power and temperature of the motor isn't exceeded during the maneuver. Here you can see a motor driver. It's connected to the avionics computer via a standardized bus, such as the CAN bus or space wire. The output of the control loop for each wheel is sent to the corresponding driver. the motor can't be powered directly with the current of the board, and thus power electronics, usually leveraging MOSFETs, are used. A frequently used component for motor drivers is the so-called H-bridge. The H-bridge consists of 4 power transistors which can quickly reverse the flow of the current, inverting the direction of the motor. This component is mainly used for DC servo motors. Several of these H-bridges are combined to control brushless DC motors. As you can see here in green on the bottom, when the motor moves, each of the different windings or phases is turned on and switched on and off at different times, resulting in the continuous motion of the motor. Stepper drivers are built a little bit differently. Here you can see an off-the-shelf variant from Pololu. On the bottom right you see a screw. With this screw you can adjust the voltage at which the coils will be magnetized and thus control the maximum torque the motor will have. To be able to microstep the motor, the coils have to be not only be turned on and off, but also only turned off a certain amount of the maximum power, allowing for the rotor to stay in between 2 actual steps. The driver has to implement this microstepping functionality, as the motor will only be magnetized passively by the driver. Now that we had looked at the individual components of motors and rovers, let's combine what we have learned by looking at an example. What you can see here is the adapted schematic of a unit project I was working on. On the top left you can see the battery, which was a 2-cell LiPo battery and had an output of 7.4 volts. The controller, driver and main processor all required a 5-volt input. The 7.4 volts of the battery were converted to 5 volts by a DC-DC buck converter. The main processor received its signal via Bluetooth and passed this high-level command then onto the motor controller. In a real rover, the motor would get his commands not via Bluetooth but over its high-gain antenna, and have way more autonomy and not simply pass on these commands that were sent to it. The motor microcontroller then aggregates the data of the individual motors, their individual current position, temperature and torque, and translates the high-level command it received into a PWM signal, which then gets passed on to the individual motor drivers for the individual motors of the rover. This can be easily implemented in PWM, and usually the motor driver is situated really close to the motor controller. The motor driver then, using the before mentioned H-bridges, generates the power for the motor in such a way that it will move according to the PWM signal it previously received. Of course, this process isn't perfect. For this case, usually the PID controller is implemented on the motor controller. Keep in mind that this schematic is drastically simplified and a real rover will feature additional redundancy, meaning that not only one single point of failure will lead to the demise of the entire system. This and several other safety considerations make the actual implementation way more complicated than shown here. This is the prototype we built. As you can see, the battery is connected and the buck converter supplies the power to all the individual components. The main computer/controller then sends a signal to the driver with the H-bridge, which then in turn powers the motor. The signal of the encoder is sent back to the controller and used for the control loop. As you can see, operating a motor is quite complicated, especially when it has to be redundant and reliable. At last, I briefly demonstrate that this construction actually works. With this last picture of 3 generations of Martian rovers, admittedly this photo was taken on Earth, I will say goodbye and thank you for your attention. I hope you learned a little bit more about motors and what you have to consider when you use them in space.